Alright, so today we're looking at lesson 48. We're looking at forces, a third equation for uniform motion, kinetic energy, and then we're going to look at dot product. So first, we're going to look at conservative forces, so hopefully you'll understand how those work. And then we're going to look at a third motion for uniform motion, a third equation for uniform motion. So hopefully you'll understand how that equation works. And then we're going to look more at kinetic energy. And then we're going to look at some more dot product stuff. So friction is a non-conservative force because energy expended to overcome friction cannot be completely converted back into mechanical energy. So friction is considered non-conservative because the energy that you have to use to overcome friction doesn't get converted back into your mechanical energy. So if you look at the picture, the man below in that picture uses a force of 88 newtons to pull a block across the floor a distance of 10 meters. And he's going at a constant speed. So the force of friction must also be 88 newtons because the block did not accelerate. So the work that he did, he moved it 10 meters and he expended 88 newtons of force. So his work is 88 times 10, so 880 joules. And the work that was converted to heat and sound by the friction was also 888 joules because the kinetic friction force equals the force equals the work that he is doing pulling this way, because those are the only two things that are in the picture. So we say that the work done by the friction was negative because the force and the distance were in opposite directions. So the man supplied 880 joules of work, and then the friction used up 880 joules of work. Okay? Gravitational attractive forces, that's considered a conservative force because gravity is always going to give back all of the work used against it. So friction is considered non-conservative, but gravity is a conservative force. So if you look at this picture, if someone lifts a mass of constant velocity by using a force of 88 newtons, you're just going to lift your mass up 10 meters. So he's going to have done 880 joules of work. He did 88 newtons of force over 10 meters. So you just multiply those. The work done by the gravity is a negative 880 joules because it's going the opposite direction. It is negative because the force and the displacement were done in opposite directions. When the man stops lifting the block's going to begin to fall. And the work done against gravity was not all used up because gravity is a conservative force, and so it'll give back work that was done against it. So whenever the block falls, all of the work that was done against the force of gravity was given back in the form of kinetic energy. And so we could use the displacement and motion equations to figure out the speed of the block. And that would tell us that all of our energy was conserved. So a conservative force is a force like gravitation or a static electric force. All of these forces are going to give back the work that was done against them. A non-conservative force is a force like friction that uses up all the work that was done against it. You have nothing to show when you move it across the floor. Like it's not going to move itself back. You move your desk over, it's not going to magically move itself back. But if you lift your desk up, when you move on, it's going to go back to where it was. It's going to fall back. So gravity is going to fix what you did. All right, so looking at a third equation for uniform motion. It is possible to combine the two equations that we know, motion and displacement, to get a third equation that does not actually contain t. So we have 2a delta x equals v sub t squared minus v sub o squared. And if you look in the book at the end of the lesson, I think they show a proof. No, they don't. thought they did. Oh wait, they do. On page 328, if you'll look, they derived that equation. So if you want to see where it actually came from, look on page 328 and then 329 at the end of this section in the lesson, and it shows you how they actually derived it. I'm not going to go through that because they work it out step by step. So anyway, if you're interested to see where that equation come from, just check out the book, okay? But they use the motion equation. The motion equation is the V, I'll write it down, V sub T equals V sub T equals V sub O plus AT. And then your position equation is X sub O plus V sub OT plus 1/2 AT squared. We don't actually usually put a delta X there, but X minus sub O is delta X, and so they would write it V sub OT plus 1/2 AT squared. But those are the equations that they're using to get this one on the board. So we're going to use the equation in an example. We've got a ball that's thrown downward from a height of 30 meters with a velocity of 20 meters per second. What will be the velocity of the ball just before it hits the ground? So we know that our acceleration is negative 9.81 because that's gravity, because it's dropped, or it's not dropped, but it's thrown, so gravity's going to affect it. The height is 30 meters, and so the change in position is going to be negative 30 because it's going to fall 30 meters. And then the original velocity is 20 meters per second, and it's actually a negative because it's thrown downward. And so we want to solve the velocity that's at the end, the V sub T. And so this is a negative 20, and we square that. So if you solve for V sub T squared, you're going to get 989, and then take the square root of that, and you're going to get 31 meters per second, and it's downward because it's going down. Okay, you can also write negative 31 meters per second. Okay, looking at another example, we've got a truck that's moving at 3 meters per second, begins to accelerate at 0.46 meters per second. How far will it travel before it reaches a velocity of 8 meters per second? So I'm going to move this over here. Our acceleration on this one is the 0.46 meters. It's not 9.81 because we're not falling through space. I mean, like around the earth. We're moving horizontally. We want to know how far the truck travels, so that's the change in position. It reaches a velocity of 8. That's going to be the ending velocity. And then the original velocity they gave us was 3. So that's the equation we're going to set up. And if you solve that for your delta x, you should get 60 meters. We only have one sig fig because we've got a 3 here. We also have an 8 there, so you just have one sig fig. So do not put a bar over your 0 or anything like that. All right, so now looking at kinetic energy defined, we can use the definition of mechanical work, Newton's second law, and the third motion equation that we just looked at, to develop our definition for kinetic energy. So definition of mechanical work, remember that work equals F times D. Newton's second law, F equals ma. And then the third motion equation, it's 2a delta x equals v sub t squared minus v sub o squared, but they solve it for delta x. And so that's what it would look like. Okay? The force in the equation is the net force on the object, which is the vector sum of all the forces acting on the object. So that means that the total work that's done on a mass by net force is going to equal the change in kinetic energy of the mass. And if you look in the book on page 329 at kinetic energy defined, they actually show you how to get to your kinetic energy formula that we've been using for several weeks and months now. It's very quick plug in with the 3 equations that I wrote out. And so just look in the book and you can see how they did that. Okay. The work energy theorem, the net work that is done on an object equals the change in kinetic energy of the object. Okay. Whatever force that you applied, whatever work you did on your object, is just going to equal the change in your kinetic energy. We remember that we defined mechanical work to be the product of the force and the distance moved in the direction of the force. Okay? So mechanical work is the product of the force and the distance that you moved it in the direction of the force. So this block, we applied 8 newtons for 10 meters, so the work would be 80 joules. Okay? In the figure below, the work done is the product of the force, which is 8 newtons, the total distance moved 10 meters, and the cosine of the angle between them, because it's at an incline. And so your work would be 8 times 10, so 80, and then cosine of theta, and then joules. And this type of product occurs so often in science that it's given a name, and it's called dot product. And a dot product is the product of the magnitude of 2 vectors and the cosine of the angle between them. The 80 joules of work from the first one is not a vector because it has no direction. Same thing with the second one. A dot product is going to be a number that we call a scalar. It does not have a direction, so it is not a vector. And we use a dot to indicate that it is a dot product. And so that little dot right there, that means that it's a dot product. So if you have F dot D, that means F D cosine of theta. Okay? So let's look at an example. A horizontal force of 20 newtons is used to push a mass 5 meters up a slope of 22 degrees. Find the work done. The distance, or we're looking for the work. Our work is F dot D. So our force is 20. Our distance is 5. And then we do cosine of 22. And so when you multiply those, you should get 93 joules rounded to 2 decimal places because we have 2 sig figs. And so the result is called a dot product. It has no direction, and it just equals the product of the magnitude of the vectors and the cosine of the angle between them. So F times D, and then the cosine of the angle that's in between those two. So that's how you do dot product. Pretty simple, really. Your homework is 1 through 20, and the curveball questions 1 through 5, so make sure to do those tonight, and then we can go over any questions you have tomorrow.